Hello everybody and welcome back to episode 2 of our series on different coordinate systems that we can use for FTC. Today we're going to be covering pseudo-odometry. So pseudo-odometry is something that I sort of made up. I'm sure somebody else has done something similar to this. But essentially, instead of using the odometers, which are essentially separate encoder wheels, this is used. You can actually run without those, which is useful because it can be run on Tink Drive, because Tink Drive and odometry don't really run well together because it's a bit more complex, because you have to do that, you have to turn and then move, and this is essentially what we're doing with this, but we're using the encoders built into the motors. So this is very useful. All you need for this is essentially just a drivetrain that can accept encoders. So pretty much any drivetrain that does not have like those tiny little Tetrix motors that need extra encoders on them. As long as you have like Andy Mark motors or Rev motors, you'll be fine because they have encoders. So let's go over some prerequisites. So the first thing you're going to need is you're going to need to at least know how to use a void method and how to do the encoder drive. So the best way I learned how to do this was you go to this in your Android Studio project. You're going to go to FTC robot controller source main Java org first inspires blah 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 all the way to external samples and then pushbot auto drive by encoder linear. So this is an example provided by First for you to use. It essentially uses exactly what you need. It shows you exactly what you need, except it uses 2 motors, but I mean it's simple enough to run it by 4 motors. You just add an extra 2, and then essentially what you're doing is that for those of you that have never used this before, this is extremely useful, the void method. The void method is essentially a separate program that you can run. So here we call on it, encoder drive. So instead of having to copy and paste this every single time we want to do something, we just call an encoder drive and put in our parameters, and it will run it. So essentially this is just going over it, and then I'm sure there's way more in-depth tutorials on this, and I am not an expert on this. I just follow the tutorials and I sort of understand what I'm doing. And I've used this exact layout for not only moving forward and back on a drivetrain, but turning also, which we'll see later. And also I've used this for an automatic lift system, where all the driver had to do was press a button and it would go up to the next height. This was during Skystone. And essentially use the motors in that ran the lift, the encoders in there, to calculate the height that you want to go to, and it was pretty quick. So next so once you have that, we're gonna want to make an encoder turn. So I'm gonna put a link to this in the description so you can copy it. Essentially what this is doing a calculation. You're gonna want this for what you're doing. So how this does it is you're using the gyro and the rev, and you're just running we're just essentially moving with the gyro to certain angles and then getting the values and then averaging them, and then we do that for 10 degrees, 15 degrees, 30 degrees, 45 degrees, and then 90 degrees. Then we just average that all up, and then you can see up here that I recorded. So our 90-degree average encoder value is 936.45, and 1 degree was 10.405. So essentially that's what we were reading on average. And then you can see here, this is going to be in the description, so you can just copy this and you're going to see how it works. It's very simple. You're essentially just doing public void encoder turn, and it's essentially the same thing as encoder drive, but instead of running forward, you're just essentially, instead of adding all these, we're just subtracting some of them and we'll run to position. So after that, once we do that, time to move on to our pseudodometry. So like I said before, pseudodometry is essentially turning to the angle you want to go, going in a straight line, and then turning to the angle you want it to be. Because sometimes when you have to turn, you go to a weird angle that isn't really useful, and you don't want to calculate it. So essentially, this is what all this is, and it uses a bunch of other functions to do this. And this uses a lot of trigonometry and math. It's not very heavy on coding. I'd say we're using essentially the same things, and most of this can be Googled if you don't understand it. Especially the trigonometric functions like the math dot, the degrees and stuff like that. So let's run right into it. So the first thing, this is the heart of it. So we can go up here and notice that whenever we want to run to a position, we just say run to coordinate, and then we have our parameters. So our position is -13, 18, and we have our speeds. So we can see here that we have our wanted position X, wanted position Y, our move speed, wanted angle, and turn speed. So this is going to be our heart, and where everything kind of branches off into the different calculations it needs to make to run. And also the encoder turn and encoder drive functions. So let's get right into it. So the first thing we do is we calculate our base lengths. So essentially, we're just making a triangle with the length that we're using. So A is essentially leg A, which is our horizontal one. If you look at a triangle, there's a horizontal and a vertical leg, and then like the hypotenuse. This is basic trigonometry. Essentially, you're just running this, you're just calculating our wanted position minus our current position, which is pretty basic. If you're at 10, if you want to go to 10 and you're currently at 1, then you just subtract 10 minus 1 is 9, and that should make sense to you. Double B, same thing, and double distance. So essentially, we're going to go to this function, which is actually right here. And essentially, is because I didn't want to type this all out in here, and I thought I would have to use this later. I didn't have to, but you know, it's there. It's essentially using a squared plus b squared plus c squared. A squared plus b squared equals c squared. And essentially you can see this, so math.pow a to the power of 2 plus blah, 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 and then you take the square root of c. Boom, and you return base c. And that's our distance. So that's essentially, our robot's going to be moving along that line because it's moving along the hypotenuse of our triangle. So now we need to find the angle we need to turn to get in line with this. So we run to get angle error, and this one is essentially, I'm not going to run through all this because it's pretty difficult to figure out. There's some logic in here, and it's mainly for if you have to move in the negative y direction relative to the robot. So essentially we have the tangent of theta. So theta is the angle we're going at. We just divide base A by base B, so opposite over adjacent. Double theta, so this is our angle. We find the arctangent of our tan theta. Ignore that. I tried to use cosine at first, and I guess I never changed that. And double target, we just change our arctangent because this is giving it in radians, 2 degrees, and then that'll give us our target. And then our angle error right now is 0. And the first thing we want to find our 0 error, which is pretty simple. It just sets the negative current angle. It gets the negative current angle, and that's how we're going to use later on to get back to our 0. So our double final target is going to be some math right here. I'm not going to go into this. It's just like I said before, running into quadrant 3 or 4 relative to the robot. So think of the robot as 0, 0 on a moving plane, on a moving XY plane. This is essentially the quadrants, because you should know this. You have quadrant 1, 2, 3, 4, and 3 and 4 are negative quadrants in terms of Y. So we go through that for quadrant 3. We just do some math, and essentially notice here that we're just changing plus minus, and then angle error equals final target minus current angle, and then we negative this, and then we return our angle error. And this is if it's positive, so this is quadrant 2 or 3, quadrant 1 or 2, and then we just find our angle error and then return angle error. And if none of that applies for some reason, then just returns to the angle error, which will give it 0, which will give an angle error of 0. That's why that's there. So now we go back up here. we got our angle error, and we're gonna turn to that. So we set that turn angle, so then we do use our encoder turn. We have our speed that we defined up here and our angle we just defined. We're going to use that, and we're going to run down, it's right here, encoder turn. You're just going to run through this. You're going to come back up here. And then you're going to want to move to a wanted position. So this is just a basic encoder drive move speed, and then distance, which is our hypotenuse, which we just turned to. So now we want to return to our wanted angle. So we notice up here we define a wanted angle. So say like I want to end up at negative 1318, but to do that I have to turn like 29.37 degrees. That's not, you don't want to have to calculate that every single time. So this just takes the trouble out of it. You just set the wanted angle you want to end up. You could be 90, 30, whatever you want, and it's going to calculate it. Usually it's 0, because like, or 0 or 90 you want just facing like the foundation or something. What you're going to do is we're going to run through get angle error and wanted angle error, which is very similar to before, but except it's a bit simpler since we don't have to calculate so much stuff. Then we just turn with our turn speed, and then current angle equals wanted angle, and then we set our positions. So I will warn you, the one disadvantage to pseudodometry is that unlike real odometry, you aren't actually tracking the encoders, because the encoders aren't actually moving around in on the field in an XY fashion. They're moving around on the field in a diagonal fashion, and it's built into the motors, so it's a lot harder to track. So you could actually end up several inches off. So it's really some trial and error, sometimes adjusting. It's not really super duper precise like an odometry system is, but this does make it simpler to do some things. But that's the main disadvantage, because we're setting our wanted position, which is what we told it to go to, not what it actually is at right now. We set that to our current position. So that, I would say, is a big minus for this, but other than that, I mean, I think it runs pretty well. I mean, it's really basic. It's just essentially a lot of math to figure out what angle to turn to and how far to go. So then we can see how we use it up here. We move forward, and then we run to our coordinate position. And since the encoder turn can sometimes be a bit inaccurate, we can adjust with our gyro. Usually with encoders, sometimes they'll slip and you have to adjust. So we just run that. And yeah, so if you want to see an example of this, I'll put a link in the description to our full GitHub repository, which has all our code. Most of this isn't going to be very useful. It's pretty basic stuff. But do keep in mind, we are currently working on an odometry system with true odometers. So just keep an eye for a video on that soon. It is getting coded right now, so just keep an eye on that and we'll get on running. So hope you enjoyed it, and see you in the next one.